Okay, my friends, we're going to be looking at section 7.8 from our notes packet. If you do not have your notes packet, that's perfectly fine. I understand that many of you either have it left at school, it's magically disappeared, your dog ate it, so on. It's quite all right. This unit, we're only going to be using the finishing up using the notes packet. Probably next week, we're going to be doing a whole bunch of brand new stuff. I'm using an iPad and a whole bunch of other cool stuff, and it's going to look just like a blank piece of paper. But for today, we're just going to finish up with the material as it's kind of designed already. So if you do not have the notes packet, you can go into Jupyter. You can print it out in that way. If you don't have a printer, once again, it's perfectly fine. You can use a blank piece of paper. Just remember that you can always, 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 always pause the video. So what we're going to be looking at today is something called trigonometric ratios, or trigonometry. And it's essentially the study of the comparison between the relationship of side lengths and angles. Use trigonometry, we're basically relying upon things like the angle within a triangle, a 90-degree angle as well, and at least one side measurement, and we can kind of go from there and dictate all the different lengths around a triangle. The first thing I want to show you though is how trigonometric angles come about, or how we can prove that there's consistency. Because in theories, within science class, math class, we have to reproduce our information. What we're going to do here is show you that there's consistency here. There's validity in this concept of trigonometric ratios. So first thing that we're going to do is look at these two triangles that are present on the paper. We have triangle ABC and triangle DEF. What you'll notice about both triangles is that besides being drawn perfectly straight, that they have two 90-degree angles in our corners and a 35-degree angle. My first question for you is, what is going to be the value of that missing angle in the corner? To find the value of this corner, we're just going to do 180 minus 90 minus 35. And using our triangle sum theory from way back in the fall, we're going to find out that the final value is going to be 55 degrees. So we know that all three angles are congruent in this figure, but as just by looking at the triangle itself, we can tell that they actually don't have the same size. So we can express them as being similar, but we can't express them as being congruent. Congruent requires the same exact side lengths. Similarity, or what we call a similarity, requires that we have at least two angles being similar, because two angles equals three angles in the case of a triangle. When we have similarity, that means that our sides are proportional, in such that if we start to set up fractional statements associated with the length of these sides, or like those equivalency statements we did back in the day where we had like triangles cut in half at its mid-segment, or we had triangles with scale factors, we're able to show that if we set up like fractions, say like BC over AC, like 2.2 over 4, and we got a number like 0.55 because we round it to find these little measurements here. If we find the same corresponding sides in our other triangle, which we can say is EF over DF, or 2.9 over 5.1, we end up getting a number that's about the same. Normally, if we were to compare, say, like AB and AC and DE and DF, we'd end up getting values that are identical, in that both of these statements here would end up being equal to 0.8. We end up getting slight variations here just because of the original method for finding the lengths of these sides are rounded to the nearest hundredth, and we end up getting little misses here. But if we remember back to scale factor, or like those questions about the 16 by 9 television, we know that as long as we have similarity, or like proportionally related sides, that if we set up equations where such that we consistently say BC over AB, and we use the same corresponding sides of EF and DE, we're going to get basically the same number. The reason why, or if you look towards question part B, the ratio of side lengths we calculated should be equal, or why is this equal, is because these sides are corresponding and similar. And the symbol that we've used for similar in the past was our tilde. We can also say because they are proportional. So if we're to go ahead and try and find the values of the figure along the bottom, triangle RST, what we have to take in consideration is what other triangle can we relate to it that's similar. Just so happens to be that this triangle here is also another triangle with a 90-degree angle, a 35-degree angle, and that missing 55-degree angle. That means we can set up another set of proportions that allows us to find the value of, say, our missing side of x and our missing side of y. One of the ways that we can set up an equation here, we can say, let's take our side AB, which we know is measured at 3.2. We're going to do AB is 3.2. We're going to find our corresponding side in our other triangle here. If we think about the orientation and all that, we're going to say that RS is going to be the equivalent to AB. We'll say that's 18. We're going to set that statement up and set up a fraction. Now we want to find, say, our value of x. Our value of x is going to correspond with side CB. So let's set up the next set of equation. CB, or BC, is going to be equal to 2.2. And our side of TS is going to be our x. We're just going to label that here as CB over TS. If we're to go ahead now and solve for x, all we're going to do essentially is cross multiply. We're going to do 3.2 times x, which gives us a value of 3.2x. And our value of 18 times 2.2 is going to be 39.6. All right, so now I want you to take a moment and go ahead and solve for x. All right, so if we're going to go ahead and solve for x, we're going to divide both sides by 3.2. And we get a final solution of 12.375 as equal to our x. And in our question, we're told to round to the near tenth. So that 7 is going to round over to that 0.3, and we'll get 12.4 as equal to side TS. If we want to solve for side RT, we're just going to set up another proportional statement. What I'd like for you to do right now is solve for side RT. If we're going to solve for RT, we're going to have to figure out in our top triangle which side is going to correspond. In this particular one, we're going to say that side AC is going to correspond with RT. So first we're going to do is set up our statement. We're going to say that AC over RT, which we're going to call Y for now. Sorry, we'll write that down next. And we're going to say that's equivalent to, we'll do the same thing here as AB over RS. If we go ahead and fill in all of our values, we have 3.2 over 18 equal to 4 over y. All right, so now your task is to go ahead and solve for y. All right, so If we go ahead and cross multiply, we end up getting 72 equal to 3.2y. And we get a final solution of 22.5 equal to y once we divide by 3.2. All right, so if you got your notes packet, turn to your next page, or if you're just using loosely, if you want to slide over to another page. All right, so now we're going to go to the second section here. This is where we start to talk about trigonometry. Trigonometry, as mentioned before, is the study of the relationship between the side lengths of a triangle and the angles in a 90-degree triangle. We're going to use some new concepts today to kind of express this relationship. The first one that we're going to do is something called theta, which you can draw as a circle. You can kind of draw it slightly as a tilde or almost like a cyclops. Some people draw it almost like a little bow tie symbol in the middle of their circle. But theta is a reference symbol. It basically is dictating which angle we're going to be talking about when we're setting up these new types of equations. All right, so when we're talking about trigonometry, there's three different types of relationships, or three different ways we can express the relationship between an angle and a side. What we're going to do is in our graph that we have, or a triangle that we have here, and that you should be writing down on your page, triangle ACB, we're going to use angle A as our reference point, and we're going to put this little theta symbol there. The way that we're going to go ahead and now label our triangle is we're going to express with regard to angle A. With regard to angle A, we're going to say that this bottom side, where CB is, we're going to call opposite. It's going to be opposite our reference angle. As always, we have our hypotenuse, which is going to be opposite our largest angle. And lastly, we're going to use a term called adjacent. And adjacent is going to be the angle that's touching our reference angle. That's not the hypotenuse. Okay. So, there's three different systems that we can go about finding the value of the sides here. The first one's going to be called sine. You might have seen on a scientific calculator, or like if you have an iPhone, your calculator, like on your phone, iPhone, Android phone, or just a regular calculator you might see at school. We have, in our scientific calculator, we have these terms called sine, cosine, and tangent. These are basically, it's a complex number system that our calculator knows, but it allows us to input degree measures, or our reference angle, and calculate values. The way that we're going to go about understanding this first, though, is that if we were to take sine, use that fancy sine number and multiply it by our angle, say like angle 35, or more specifically like angle 22, it's going to be equivalent in our triangle always, always, always to the opposite length divided by the hypotenuse. One of the cool geometric tricks discovered in the 3rd century CE. So if we're going to do this as just the segments of our triangle, that's going to be CB over AB. Cosine theta is always equivalent to the adjacent side over our hypotenuse, which is equivalent to our sides AC over AB. Lastly, we have one tangent. Tangent, you could say, is the only one not using hypotenuse. That's always how I remembered it when I was in school. And we have opposite over adjacent. is CB over AC. When I was your age, way back when, we had this acronym that we used called SOHCAHTOA. And while you're stuck at home with your parents, grandparents, whoever, you can probably ask them if they've heard that term. But SOHCAHTOA is an acronym. It stands for sine OH, so CAH, C-A-H, TOA, T-O-A. So it's a mnemonic that you can use basically as a means of memorizing the order or the sequence of these concepts that are here. All right, if we're going to apply these terms with our try it out section here, let's take a look. So here we have triangle ABC, and we're asked in this first example to use sine theta A, or sine reference angle A. So in this particular example here, we're going to say put our theta in the bottom left-hand corner, and we'll have our opposite side, we'll have our adjacent side, the one connected to our 90, and then our hypotenuse. Sine A is going to be equivalent, if we're looking at our opposite of 1, over our hypotenuse of 2. Cos A, or adjacent over hypotenuse, is going to be radical 3 over our hypotenuse of 2. And tangent, which is our opposite and our adjacent, is going to be 1 over radical 3. Next, if we're going to talk about sine C, as in C is going to be our reference point where we decide where our opposite is, where our adjacent is, where our hypotenuse is, sine C is going to be equivalent to radical 3 over 2. All right, so now I want you to take a look and see what you think cos C is. Cos C is going to be the same as our adjacent over our hypotenuse, and that's going to give us our adjacent over our hypotenuse. Remember, hypotenuse is always opposite the largest angle. For tan, or tangent, as the longer name is, tan C is going to be radical 3 over 1. And remember, you can always pause the video if you want. Nice thing is you can also rewind as well. Question number 2 says, in the following diagram, triangle QRS has side measurements of QR being 8 and QS being 7. We're being asked to find the value of sine Q, as in Q is going to be our little reference theta, and we want to find our answer. Sine Q is going to be equivalent of our opposite over a hypotenuse, which is going to be equivalent to SR over our hypotenuse of SQ. If we go ahead and insert the values, we end up having an unknown for SR and a assigned value of SQ for 17. All right, so we have unknown variables here. In theory, Q has an actual measurement. Like if we had a protractor, we can go ahead and measure our angle there. But since we don't have the measure and we don't know the value of x, we're kind of stuck. There is another way that we can technically find out the value for SR. Particular example, we do have a right triangle, so we could use our Pythagorean theorem to find the value of our side x. So if we were to use Pythagorean theorem, which is a squared plus b squared equals c squared, we can say that we have 8 squared plus x squared is equal to c squared. 17 we know being c because it's the opposite of our 90-degree angle. It's also our longest because it's opposite of our longest angle. We go ahead and just punch out our values here. We get 64 plus x squared equal to 289. If we subtract 64, we get a value of x squared is equal to 225, or we radical x squared, we get 15. So sine q, we can say, is equal to 15 over 17. All right, and our last question here for our note section for today. We are told that triangle ERM is similar to triangle JTM. Which statement is always true? All right, so essentially what we're looking for is basically if we're going to use cos J or say tan E, we want to make sure that the sides being referenced here for opposite and our adjacent, for instance, are going to be the actual correct ones listed. So the first step that we have to do, the actual theory here or the trick here, is that we're going to have to position both triangles in a fashion which makes them look like they're pointing in the same orientation. The way that we figure that out is we have to kind of remember in regards to orientation is what's going to be like our longest side, our shortest side, and our medium side. So we always know that the side opposite of our 90-degree angle is going to be our longest, which helps us out. So we're going to know that M and M are going to be corresponding, but do we know if, say, T and E are corresponding and J and R are corresponding? One thing that we can do is if we start to rotate our page, we can try and see which side's going to be longest. If we have it pointing up this way, we can see that JT being our hypotenuse, we probably have our smallest side and then maybe our medium side. If we look clearly at RME, we have our hypotenuse, we have probably our medium side, and then our smallest side. So if we actually match these up, we can say that we have a triangle TMJ. Corresponding with RME. So now all we need to do is figure out essentially which equation here, which equation down here is going to be set up properly. We're going to end up, if we just plug through everything, we end up getting a value of D. But to kind of express that for you, tan E, which is going to be equivalent to J, would be our opposite side of TM, and our adjacent side of JM. So tangent, just as a reminder, is always our opposite over our adjacent. All right, so for your work to complete this particular section, you'll see in Google Classroom is a file that has all of the questions for the independent practice for 7.8. You are to finish those, get some good practice in. There's some variation there for you to set up of these 3 different try it out sections I just showed you. Once you finish that, you can go on to your exit ticket. Your exit ticket is also going to have a set of instructions on how you can actually go ahead, input those answers, and show them to me. Once you finish that, I would suggest you then go right on to section 7.9. 7.9 is going to be a bit faster, but it's also going to relate directly to what we just went over.